we'll now be looking at transformation of trig functions, which again is something that you've done in grade 11, only you were working with degrees, not radians. And we're also going to be applying transformations, but keep in mind that with trig functions, it doesn't look exactly the same as it does with other functions because we have these key characteristics that we focus on. We can still think of them in terms of transformations, but I find that it just feels a little bit different in terms of the approach that we take. However, I still wanted you to recall what the different constants mean because they still apply to trigonometric functions. So you can simply just review these. These are the same constants that we've been using since the beginnings of grade 11. Now, for the minds on, I'm going to have you start thinking about some of the skills or the knowledge that you have coming out of grade 11. And so the first thing here is just to ask that you identify these characteristics for each of these functions and also label these characteristics on the diagram that's provided. So if you would just take a moment and do that and then come back and see if you're right. For this first function, a is the number out in front of the trig function, and that tells us the amplitude. Although keep in mind the amplitude is a positive value. That's the distance that the max and the min are from the axis around which the sinusoidal curve oscillates or goes above and below. So the amplitude here is 3. The period is equal to a full circle because with the parent functions, in this case, the sine x, now with the 3 in front, it's not a parent function, but this sine x on its own, because there's no k value in here, the period is 1 full circle, which is 2 pi. And the equation of the axis, and remember it is an equation, so you need a y equals. Because there's no vertical translation, there's no c value here. So there's no constant out here that adds to the y value to translate this up or down. Therefore, the x-axis is the equation of the axis, so it's y equals 0 for the equation of the axis. And I'm just going to label this as the axis. So looking at this function here, y equals minus 4 cos 2x, the amplitude is 4, not minus 4, right, because it's just a positive value. The period, now this is a good time to remind you that the period is equal to the period of a parent function, which now we're talking about 2 pi as opposed to saying 360 degrees divided by k. Similarly, the k value in the equation is equal to 2 pi divided by the period. 2 pi divided by the k value, which is 2, gives us a period of pi. Or we could say this is a horizontal compression by a factor of a half, right? 1 over. Happens in the inverse way, right? Inverse manner. So a half of 2 pi is pi. And the equation of the axis, once again, there's no k value. So the axis is y equals 0. And I said no k. I should have said there's no c value for the vertical translation. Looking at this function here, the amplitude is the comes from the a value out in front, but absolute value, right? Positive. So the amplitude is 10. The period is 2 pi divided by 1/2. Invert and multiply, that's 2 times 2 pi, so that's 4 pi. Or we could say it's a vertical stretch by a factor of 2, and 2 times 2 pi is 4 pi. And once again, there's no c value, so the axis is y equals 0 in this case. And finally, this last function, which is simply in terms of cos, but similar to this function here, where there's only the a value that's transforming this function. So the amplitude is 2. The period, because there's no k value, the period is equal to 2 pi. And once again, it's true for all of these. There's no c value or vertical translation, so the axis is y equals 0. What we have here is a sine function. It could be a cosine, remember, if you think about your transformations in terms of phase shifts. In this case, if we were writing the equation for this, think back to grade 11. This axis here is y equals 2. At the y-axis here, the function starts on the axis, which is like a sine curve, so it would be easier to write the equation for this in terms of sine. What we want to do is label where the amplitude is. So the amplitude goes from the axis to the peak of the wave. So this is the amplitude right here. The axis is, as I mentioned earlier, where this y equals 2 is. Halfway between the peak or the maximum and the minimum. That's the axis. And the period is represented from one point on the curve to a corresponding point on the curve where we've gone through all the possible values of y. So we could label this period at various points. I could start here and then follow that through and end here and show that as the period. I'm going to go peak to peak in this case. So from here to there is the period. Those are the key features that we want to be familiar with as a reminder as we work through these. Now, in this next step, what I've done is, again, to start with some reviewing, we want to practice writing equations. Already, it's going to be new to you in that you're going to be using pi, and notice that the axis is labeled in terms of pi, right? So the x-axis here, pi over 2, pi, 3 pi over 2, full length here, or the full period, not period, but the scale goes up to 3 pi. Now, in some of these instances, I'm trying to keep it simple to get you back in the idea of applying your transformations. So in this case, I've only put in one transformation here. And in each of these, the red function is the parent function. So what we're dealing with right now is a sine curve. And then we're transforming it. In this case, it's a vertical translation. And once again, I would encourage you to take a moment and pause the video and try these on your own, and then play the video and see if you've got them right. So in this case, we're starting with a parent function that's a sine curve. So y equals, the amplitude is 1. So I don't need to put any number out in front. The period, looking from, say, here to this point, is 2 pi. So there's no k value. There's no phase shift because it starts at the axis, like a normal sine curve. So the only part here is this translation, and the axis is a good reference point because it starts at 0, right? It's y equals 0. So the vertical translation here is 2. So we have y equals sine of x plus 2. Looking at this cos curve, here it starts as it would at a maximum on the axis, so that's a cos. And then looking at this blue graph, what we have here is a transformation, a phase shift, or a horizontal translation. This original curve starts here on the axis. So now what we want to do is write this in terms of this cos being phase shifted. And there's different ways that you can look at this. You could also reflect it. For example, if I took this cos curve and I phase shifted it pi over 2 to the left, which would be a plus pi over 2 in the equation, then this curve, if I take this and translate it this way, would be going down. So that's a negative or a reflection. If I don't want to add a reflection, then I would take the original curve and find where it starts at the same place as this blue function. So that would be right here at 3 pi by 2. So I would want to phase shift the 3 pi by 2 to the left. So that's a plus 3 pi by 2, and then I would not need to do a reflection. So that's what I'm going to do. Y equals, and again, the period is 2 pi, and the amplitude is 1, so there's no other changes. Y equals the cos of bracket x plus 3 pi over 2. And again, that would phase shift this red function to the right, to the left, I mean, from here over to here, so it would line up with this blue graph. Looking at this function here, once again, the period is still pi over 2. In this case now we see that the amplitude has changed. They both start at the same place on the axis, so there's no phase shift. So all there is a vertical stretch, or an amplitude of 2. y equals, and we're starting now with a sine curve, so 2 sine of x. And finally, looking at this graph here, once again, the amplitude you can see readily is the same for both of them, and it's 1. They're both cos curves, and they start at a maximum. So the only change here is the fact that there is a k value, or there's a different period. So in the original function in red, it's 2 pi, but this function has a period of pi. Now we could quickly see there that that's half, so the k value would be 2, because remember they have the opposite effect. Or you can use the equation or formula and say that k is equal to 2 pi over the period, and the period of the new function is pi. So that makes the k value 2, which is what we just noted. And that would be a compression horizontally by a factor of 1/2. So the equation then is y equals cos of 2x. All right, so that's a quick review of the basic transformations, all separated on their own. And again, we are now using radians, so we've been working with 2 pi and other multiples of that. Now what we can do is extend this to writing transformations and also then writing equations. And once again, I don't have an example of writing equation that I would necessarily do with you together because you did learn how to write equations in grade 11. We've gone through all the separate components, so I'm hopeful that you would be comfortable putting them all together and having more than one transformation here as you write the equations, and also being able to phase shift between sine and cos, and so write this function in terms of either of those parent functions. And then the other step here is to try doing that with a table. Quickly though, we are just going to review writing the transformations. This is a reflection, there's a minus in front, so it's a vertical reflection in the y-axis. So it's a vertical reflection in the y-axis, or over the y-axis. It's a horizontal stretch. There's a 2 out in front, so it's a vertical stretch, pardon me. A vertical stretch by a factor of 2. Looking at this 3, remember these happen in inverse. So it's the opposite operation, or the other way of looking at it is that for horizontal transformations, the relationship is 1 over k. So that's for horizontal stretches and compressions. So looking at this function, this is a horizontal compression by a factor of 1/3. And remember, the factor is what we would multiply the parent function by to get the result. So that's how you remember what to put here, right? We would multiply the parent function's x values by 1/3 because this is a compression. And finally, there's there's a phase shift also. So here's a phase shift. And remember, this happens in opposite, so that's to the right. A horizontal phase shift. Of pi to the right. I'm running out of space, so I'll just put of pi right. And finally, the 3 at the end, there's a vertical translation of 3 up. Coming over to this next function, there's no reflections, but there is a vertical stretch. I'm going to use a short form here since I have less space. A vertical stretch by a factor of 5. Looking at the 4, now here's where we need to be careful. I see it now. It's not going to affect me till I get to this -5 here, this d. But I do need to factor out that 4. So now that I've just noticed that, I'm going to do it right now. 5 cos. If you look back to the first sheet that I gave you that reminds you of the various constants, you'll notice that in the general transformation function at the top that the k is factored out. So I'm going to factor out this 4. I'm going to put a square bracket and factor the 4 out. So that leaves me with an x here, and then if I divide -5 by 4 and then I leave it as a fraction reduced, it's just simply -5 over 4. And then I have this -2 out here that's unaffected. So first of all, dealing with the compression, that k value, it's a horizontal compression by a factor of 1/4. Then the translation, which was affected by that 4 being factored out, it's not -5, or pardon me, plus. It's a horizontal translation of 5/4 to the right, or a phase shift, which is what we use when we're talking about sinusoidal functions. A phase shift of 5/4 to the right, and I'm just going to put right again because I'm running out of room. And then the -2, which is a vertical translation of 2 down. And remember the y's, which are outside the function, right? They happen directly. We're taking the output of this function and multiplying by 5. So all the y's will be 5 times bigger compared to the parent function. We're taking the output of this function, we're subtracting 2. So they will all be 2 less compared to the parent function. Whereas inside the bracket, these affect the x. And so they have the opposite effect. I call these sometimes either a helper or a hindrance because, for example, if I just focus on this 4, if I multiply the x's by 4, that's really helping the input because it's going to be 4 times bigger before you input it into the function. So these x's compared to the parent function would only have to be 1/4 of the size if I'm focusing just on this 4. Now there's also effect by the 5/4 as well. So this is a vertical translation of 2 down. So that's a review of simply identifying the transformations based on the constants that you've been given. And now what I would like to encourage you to do is go ahead and try this consolidation. I recognize that using radians, we haven't put all of these transformations together in one question, but I think with your experience from grade 11 and the fact that we just reviewed them individually, that you would be able to do this on your own. So give that a try. Now, in order to write the equation for this, we basically need to find all of the constants in this question. So one of the first things I usually will do is draw my axis. So this goes from -1 up to 5, halfway in between, 1, 2, 3, 4, 5, 6. So halfway in between is at 2. At this point, I am going to remind you that there is a formula for the axis. So for the axis, that would be y equals, now think about the fact that this is an average, right? It's in the middle of the maximum and the min. So an average is when you add the two numbers together and divide by 4. So you could use this formula, although on a graph it's quite straightforward because you're just looking at the halfway point. In a table, it's not quite as easy, although you can think of it that way as well. So the axis would be y equals the max plus the min divided by 2, which is the middle or the average between the max and the min. Now looking at this graph then, we need the amplitude, which is 2 to 5, so that's 3. So now I'm just going to write my a instead of the amplitude. So this is not reflected, so a is going to be 3. By the way, right now, because it starts at a maximum, my first thought is to focus on this cos here, and then do the sine after with the phase shift. They will have similar constants, except for the fact that there will be a d to do a phase shift. So we have a equals 3. We already know that the axis is y equals 2. So if the axis is y equals 2, that means that our c value is 2. And then looking at the period of this function goes from here, let's say this peak to that peak is pi, right? So we could look at that and say, well, the k value is 2 because that results in a compression by a factor of 1/2, or we can write that k is equal to 2 pi, which is the period of the parent function, divided by the period of this function, which is pi, and that leaves us with k equal to 2. Now I can write my cosine function y equals, amplitude is 3, cos, and the k value is 2, so 2x, and a vertical translation of plus 2. So there's my equation written in terms of cos. Now in terms of sine, I'm going to need a phase shift. So when I'm looking at this function, I'm first of all thinking about a sine function starting over here at 2, a parent function. And I want to translate that sine function on top of this one. So to do that, if I go this far, I'm going to have a reflection. I'm going to go this far and write it without a reflection. So now I need to know what that value is. It looks like it's halfway in between. So pi over 2, this is pi over 4. Remember, we're taking pi then and dividing it into 4 parts. So that's 1, 2, 3 pi by 4 is the phase shift. And it's to the right, because I'm starting with a parent function here and moving it, translating it to the right. So that's a phase shift of plus 3 pi over 2, right? So my value or my d value, or inside the bracket, inside the bracket with the angle, I will have a minus 3 pi over 4. So d is equal to 3 pi over 4. Now you don't necessarily have to write this. Sometimes people find this confusing because they get used to switching the sign when they write the function, that it's the opposite sign. In this case, if you look back at your constants on the initial page, d is such that because the transformation function has a minus in front of the d, that whatever number this is relates to the direction you're moving. So here you're moving a positive 3 pi by 4, or translating a positive 3 pi by 4. Now, if I write the equation, you'll see better what I mean, that this is 3 cos 2. Everything stays the same, keeping in mind that I wanted sine here. Sine, I'm going to put a square bracket, and then here I have this bracket, and it's going to be x minus 3 pi by 4, right? So normally we just think it's going to the right, so we're going to have an opposite sign here. But in terms of the constants, they write the general transformation function so it already has a minus here. Normally I won't write this part here. I will simply write it in here and think about the fact we need the opposite sign, and then still this plus 2 is the same. So there's the two possible equations. Now, just so that you recognize how this can be done, remember we mentioned that if we did a phase shift to here, which is pi by 4, that we would have a reflection. So the equation there would be y equals minus 3 sine of 2x minus pi by 4, because it's translation to the right, or a phase shift to the right, and then plus 2. So there's 3 possible equations of an infinite number that we could write, because we could phase shift this any amount that we wanted. Finally, let's look at this table. Sometimes people find this a little bit more difficult. Keep in mind, though, that you could always just draw a sketch. If you're comfortable drawing them from the graphs, then one idea is to simply take this and draw a quick sketch on the side. Graph paper isn't necessary. Just in that white space there, you could draw a sketch, and that would help you. Or you can reason out the characteristics. So first thing I do is look to see where my mins and maxes are. So minus 3, 1, minus 3, 1. And it doesn't hurt to label them. So it looks like this is my minimum here, and this is actually my maximum. One thing to think about is min to max is only halfway. Then we're going back to minimum again. There's the period. So the period is 4 pi. So knowing that the period is 4 pi, then my k value is equal to 2 pi over 4 pi. So that leaves me with 1/2 as my k value. This is a horizontal stretch, or by a factor of 2. Now my axis, this is where the formula could come in handy, right? The axis is halfway in between. So I could simply do my formula, or you may already have thought of what's halfway in between here. Y equals the maximum or the minimum, it doesn't matter which one you start with, since we're adding, minus 3 plus 1 all over 2. That gives me minus 2 over 2, which is minus 1. Then I want to make sure that that's really halfway in between. Minus 3 to minus 1 is 2, and minus 1 to 1 is 2. So that's our axis. Now, the minimum starts at x equals 0, so the minimum is on the axis. That tells me two things. One, there's no phase shift because it's starting at a natural point. And two, a cos would be the easiest to do because cos starts at a min or a max. And this also tells me that there's a reflection. So now I can go ahead and write my equation. Y equals, I said there's a reflection, and I haven't written down what my amplitude is, or my A value. Let's just write the amplitude over here. We see that the amplitude, because it goes for this -1, it goes 2 above or 2 below. The amplitude is 2. We said it's a reflection, so this is -2 cos, because it's starting at a minimum. There's no phase shift, but the K value is a half. And then we said that the axis is -1, so that makes us -1 out here. And there we've written the equation for that table. And again, if you wanted to do a phase shift, you could also write this in terms of sine.